What are algorithms? The technical definition of an algorithm is a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. For example, a real-life algorithm for a phone book search would begin with step 1, open the first page. Step 2, search page for the name. Step 3, if the name isn't there, move to the next page. And step 4, repeat steps 1 through 3 until you find the name. Now, as you might guess, this method is pretty slow, so you might try something a bit more efficient. That would begin with step 1, open the book roughly midway. Step 2, check the first letter of the name and compare it with the letter of the page. Step 3, if the letter of the name is the same, check that section for the name. Or, if the letter of the name is later in the alphabet, then act as if the right half of the phone book is a new phone book and repeat steps 1 through 3. Or else, act as if the left half of the phone book is a new phone book and repeat steps 1 through 3. As humans, tell us to search for a name in a phone book and we'll likely go for the more efficient method out of intuition. Computers, however, are not very intuitive and must be given very strict directions to execute when they encounter situations. Computers are given these directions in the form of code, which brings us to the topic of programming.
What is programming? Programming is really just translating our algorithms into a language that a computer can understand and execute. There are many programming languages out there and they all have their pros and cons. Let's take, for example, our phone book algorithm for earlier and turn it into something called pseudocode. Pseudocode is not code for a specific programming language, it's just simplified code that could be translated into any number of languages. It contains the basic idea of what the program entails without getting into language specifics. For example, the pseudocode from the phone book algorithm would go something like this. This while statement is telling the code block inside of it to keep running while the name hasn't been found. The code inside of it says if the name is on the page, the name has been found is now true because the name has been found, so it will tell the while loop to stop executing, and it will also return the name to the user, or else it'll move on to the next page. This is an example of conditional branching where programs can handle multiple situations.
Now, onto a very widespread use of programming. Many companies around the world receive a myriad of data about various things, including customer data, ad data, and other types of useful statistics. The thing is, most of this data is brought in as unorganized chunks, and for people to make any use of it, it must first be sorted. This is an example of where programming and algorithms combine to make effective solutions to problems. Just like there are multiple algorithms to search for a name in the phone book, there are multiple ways in which we can tackle the problem of sorting an unorganized data set. Some are much better than others in terms of efficiency, as sets of data get larger and larger. The algorithms we use are called the bubble sort, selection sort, insertion sort, and the merge sort.
The bubble sort works like this. We first check the first and second values. If the second value is smaller than the first, we switch them, and then we continue on through the list until we reach the end. We repeat this process until the whole list is sorted. Through this method, the biggest number will always bubble up to the top of the list. Next, we look at selection sort. In selection sort, we start out by looking through the whole array, and we find the smallest value. In this case, 1 is the smallest value. So then we take 1 and the first value, which is 8, and we switch them. Now, we have a sorted portion of the array and an unsorted portion. We continue looking through the unsorted portion and finding the smallest value and placing it into the sorted portion. In insertion sort, we take the first value in the array, in this case 8, and turn it into a sorted list. Everything else is an unsorted list. Now we take the first value in this unsorted list and we test it against our sorted list. So in this case, 5 and 8. We put 5 behind 8 and then we turn that into the new sorted list. We continue on taking the values from the unsorted list and placing them into the sorted list. Next, we take a look at merge sort. In merge sort, we take our full unsorted list and we divide it into 2 sublists. We take those 2 sublists, divide them each into 2 more sublists, with a total of 4 sublists now. We take each of those 4 sublists and divide them by 2 and get 8 sublists of 1 element each. Now, by definition of a 1-element list, the list is organized. So what we can now do is recombine these lists. The lists are recombined in ascending order. So 1 goes behind 8, 3 behind 5, 2 behind 4, and 6 behind 7. Now we have 4 separate lists, each of which are completely organized. meaning that the first element in each of these lists will be the smallest element in that list. So now we can just compare first elements every time to start combining these lists once again.
In this experiment, we use 4 different sorting algorithms to sort randomized sets of data. The independent variable is the size of the dataset, and the dependent variable is the time it takes for each algorithm to sort.
To make this experiment work, we coded up a program in Java that we give a set size to. After we give it that set size, it creates a randomized dataset and makes 4 copies of it. It passes these copies to the separate sorting algorithms and then times their respective executions. Every run, we would increase the dataset size by 5,000. Here is the dataset and its graph. Notice that bubble, selection, and insertion sort have graphs that look like they're becoming exponential, whereas merge sort looks like it's just flat. This is because merge sort eventually would become a graph known as n log n, whereas the dataset increases, the time taken to sort really doesn't increase that much at all. Looking at the data, we can very easily conclude that merge sort beats out all the other algorithms in terms of sorting large sets of data.